Hey, welcome to Chapter 6. This is going to be a pretty easy and fast chapter because I think most of the ideas, surface area and volume, you already know, and you might have even encountered arcs and sectors of circles before. So let's get right to it, shall we? The first thing I want to discuss is just what is in the formula book for the whole chapter all at once. Because you see right away here on page 2, there's actually not a whole lot that we need to have memorized. We just need to know where we can find things. So we've got a number of area formulas here, which you're likely very familiar with. The circumference of a circle. We've got some 3D volume stuff going on here. Cuboid is just a fancy name for a rectangular prism. Same thing. We've got cylinders. We've got generic prisms. And then we've got area for the curved surface of a cylinder. That does not include the top and the bottom of the cylinder, but we'll talk more about that stuff later on. And if we move forward in the booklet, when we get up to page 6 with geometry, we see more formulas here in the SL section. We've got volume of a right pyramid, right cone, and the curved surface of the cone, as well as some formulas for spheres as well. Although I should point out that it doesn't even matter whether it's a right pyramid or a right cone or not, whether it's right or oblique, they're going to have the exact same volumes thanks to Cavalier's principle. That's a topic for another time. Let's jump in to chapter 6 now. Okay, so we're going to talk about just like parts of circles here. So we have an arc, that's just a portion of the circumference of a circle. All right, there we go. And we can calculate what the length of that arc is by considering it as a proportion out of the entire circumference. So the entire circumference is 2 pi r. Right, we know that. We're going a certain percentage of the way around the circle. How many degrees are there in the entire circle? There's 360 degrees. How many degrees have we gone out of those 360? Well, whatever angle it is. In this case, we're just calling it theta. So that's why to calculate arc length, we just multiply the full circumference by the percentage of the way around that we've gone. This formula is thinking in degrees. There's another formula which I think is way simpler and better that has radians, and that's just coming in a later chapter. We'll get to that very soon, but certainly if you're comfortable thinking in radians and you know that formula, then you know that's the better way. But anyway, down below we've got a sector, and a sector is just a portion of the circle's area, as long as it is contained between two radii like that. It's like a pizza slice, right? And I want to just distinguish right now between a sector and what is called a segment. A segment would be that area there. And those do show up in IB questions often. What's the relationship? Well, the segment plus the triangle here gives us the entire sector. And again, we see that we can calculate the area of the sector by taking the area of the entire circle and then simply multiplying by whatever proportion of the circle our sector is. So we'll just look at one of these real fast here. Let's find, for this particular shape, the length of the arc, the perimeter of the sector, and the area of the sector. So we might first ask ourselves, if this was an entire circle, what would the circumference be? Well, that would just be 2 times pi times the radius. The radius is 3, so that's going to be 6 pi. And what's its area going to be? That's going to be pi times the radius squared. So that's going to be 9 pi. We're going to use those now to calculate down below. So let's just look at arc length first. We've got our 6 pi right here. We know that it's 48 degrees, so we just multiply that. Great. We get an answer. This is rounded to 3. Significant figures. A more accurate answer would have been 2.513. So we just keep it as 2.51. Next, for the perimeter, we're just going to take that arc length, which we just calculated, plus 2 of the radii. Each of the radii is 3, so we're just adding 6 to our 2.51. We're getting 8.51. And then finally, for the area of the sector, we're going to take our 9 pi and multiply that by 48 over 360. And we're going to be getting out of that 3.769 And so we're going to round to 3.77 for our three significant figures. Moving on to section B now, we're in 3 dimensions. Here we're only considering objects that have flat faces, so nothing curved. And the book likes to consider these by drawing their nets, which is just the image that you get if you imagined flattening out the entire 3-dimensional object. It's completely unnecessary. You do not need to do that. I don't like to do that, but you can if you wish. So here's an example. Here we have a pyramid. Now, it's not actually stated in the question, but this is a right pyramid. And a right pyramid, we mentioned that briefly just a moment ago, that means that that altitude there, well, it is an altitude. It's at a right angle to the plane that is the bottom surface. And while it doesn't make a difference with volume, whether the pyramid is a right pyramid or not, in order to calculate its surface area, we're going to require that it is a right pyramid so that each of the triangular faces ends up being congruent. If we had a pyramid that was, I don't know, like skewed out over here somehow, even if it had the exact same height, the volumes would be the same, but clearly those 4 triangular faces would not be congruent to each other. And we're going to require that to do the work here. So we assume that this is a right pyramid, and we move on. Now, to find its surface area, that's pretty easy. We're just going to take the area of the base, which is 13.2 squared, and then we're going to add to that the 4 areas of those congruent triangles. So that's 4 times, well, half the base times the height. We know the base is 13.2, and the height we figure out just by using the Pythagorean theorem. Notice here that the height of each of the triangles is actually the slant height, if you will, of the pyramid itself. Anyway, add up all that together and you get your surface area. But let's talk rounding just for another moment. Right here, we rounded when we took the square root. That really came out to be 12.657. We wouldn't want to round that to 12.7, even though that would have been 3 significant figures, because we're going to use that work later on. So instead, we round it to 4 significant figures, and then we use that in the next step of the calculation. And there, our final answer actually was 508.3, so we just round that down to 508. Had we used 12.7 in our calculation here, we would have gotten a final answer that would have rounded to 510. So it's really, really crucial that we not round our answers too much too early. We now turn our attention to 3 curved surfaces. Now, these formulas were in the data booklet that we saw earlier. However, in that case, they did not include, in the case of the cylinder, they did not include the 2 circular ends. And in the case of the cone, they did not include the circular base. They were only including the curved portion of the figure. It was clearly labeled as such, so that's nothing that I think you'd have to worry about remembering. The textbook does have an investigation in it for how one might derive at least the surface area of a sphere without calculus, although I certainly prefer using calculus myself. The cylinder, on the other hand, that one's much easier to see where this 2 pi RH comes from. It's because if we were to unwrap the circular, the curved sides of the cylinder, if we unwrapped it, we would have just a rectangle. And then what would the area of that rectangle be? Well, it would be the base times the height. Now, the height of that rectangle is the same as the height of the cylinder, so that's our h, and then the base, that would just be this length here, which is the same as the length around, which is the circumference of a circle, so that's our 2 pi r. Anyway, we can use these, pause and read these if you want a refresher on how to work out the surface areas of various shapes. Notice that these questions specified finding to 1 decimal place rather than considering significant figures. So it is always important to read the question to know what level of accuracy to give your answers in. and that might include writing a number with a 0.0 at the end. We turn our attention now to section C, where we're discussing volume. The book labels these solids of uniform cross-section, which I think is just a fancy word for prism. Discussed those a few moments ago. So this image here is a triangular prism. That picture there, well, if we assume that all of the angles are right angles in all 3 dimensions, then this would be a rectangular prism, also known as a cuboid. If all of the angles are right and all of the sides happen to be congruent, then it's the very special case of a cube. But more generally, if none of the angles are right, it is known as a parallelepiped, which you can imagine as just being what you'd get if you made a rectangular prism out of parallelograms rather than out of squares. Anyway, to find the volume of a prism of any type, all we're going to do is take the area of the cross-section, and the cross-section is really just the same as the parallel bases. Every single prism has 2 bases which are parallel, and then we multiply by the length, which is going to be the distance between those parallel bases. In the case of our triangular prism here, the 2 bases are going to be what looks to be the front and the back of this one, so it's going to be that triangle and that triangle. Of course, if we have a prism that happens to have multiple pairs of parallel bases, then it doesn't matter which ones we choose. We'll get the same answer all the time. And we use the same idea here for a cylinder. And this is why the book used this phrase, solids of uniform cross-section, because a cylinder is a solid of uniform cross-section. It's just not technically a prism because prisms can't have any curved surfaces. But anyway, using that, we can calculate the volumes of all sorts of prisms. So here's, again, just 2 examples really quick. Make sure you know how to do that. Great, I'm moving on now. We can also kind of work backwards. We can figure out aspects of the object itself if we know what its volume is. So there's that. Marvelous. Okay, and then we've also got other solids. These don't have uniform cross sections. They're called tapered solids. I didn't know that phrase off the top of my head till I was making this video. So, and I'll probably forget it pretty quickly too. But so don't feel like you need to know that word. So taper just means that the cross sections are going to get smaller as we get closer to the apex, which in the pyramid and the cone is just like the tippity top, and the sphere, I mean, you know, you could consider the top to be the apex, although really the sphere has infinitely many possibilities for what you would choose as the apex. Anyway, the volume for the pyramid or the cone, it's going to be 1/3 the area of the base times the height. And for the sphere, we use 4/3 pi r cubed. And again, these are formulas that can be derived through calculus, and definitely in the case of the cone and the sphere, and through other means for the pyramid as well. But we won't dedicate any time to that here. Again, these formulas are in the data booklet, so don't worry about having to memorize them. And finally, this is section D. D is about capacity. Now, the word capacity does not appear in the course guide, so I don't actually know if we need to worry about this, but it's in the book, so I figured I'd just mention it. Capacity and volume are intimately linked. One has to do with the container itself, and the other has to do with the amount of fluid that could be contained in the container. So we see some conversions down there at the bottom. If the volume was 1 cubic centimeter, then the capacity is 1 milliliter. So, you know, when you go out and you purchase a gallon of milk, it's true that you're purchasing a gallon of milk. It's not true that you're purchasing a gallon bottle of milk, or you can't purchase a liter bottle of soda. You can purchase a bottle which has a volume of 1,000 cubic centimeters, or you can purchase a liter of soda. That's the amount of soda that you're getting, but it's not a 1 liter bottle, if you want to be technical. But I don't know how much that really matters for this course, and certainly in colloquial speech, we use the terms capacity and volume interchangeably. Anyway, let's just do one problem. This is like the most interesting problem in the whole chapter. You can see there's a lot going on here. It's a whole bunch of numbers and a whole bunch of shapes and a real-world context. We got to talk about rain. So first of all, we got 17.3 millimeters of rain falling. And what does that even mean? Well, rainfall is measured by essentially by checking to see how much rain you have in a cylinder after it falls. And so you just measure the height of that rain. But long story short, it doesn't really matter how big the cylinder is diameter-wise, but that's not the point here. The point is 17.3 millimeters, that's a height of water. Now it's falling on a rectangular roof, which has certain dimensions. We can therefore calculate the total amount of water that's fallen on top of the roof by taking that area of the roof and then multiplying it by the height, if you will, of water, 17.3, and that will get us a full volume of water. All of which is going to go into a cylindrical tank, which happens to have a diameter of 4, and then we're going to figure out how high does the water in that tank rise based on the amount of volume that's going in. Anyway, let's look through it now. So the first thing we need to figure out is the total volume of water that's fallen. So that's 17.3. That's going to be multiplied by the 10 times the 6.5. And oh yeah, I forgot about this. Of course, we've got to convert everything to be the same unit. Otherwise, we're going to be running into all sorts of trouble here. So they've decided to work with meters. Doesn't matter. In fact, if it were me, I think I would have probably changed everything into millimeters, since the question is asking in the end by how many millimeters does the water level rise, but whatever, it doesn't matter. We can convert again later on if we need to. So we've got our rainfall there, and we're going to multiply that by the area of the roof to get a total volume here, 1.1245 cubic meters. Now we're going to put that into a cylindrical tank. So the tank's got a diameter of 4, radius of 2. The total volume that we're therefore going to add to the tank is going to be 4 pi multiplied by whatever the extra height of water happens to be that we add in here. So we can imagine that like this line represents the total amount of water that used to be there. We're adding in some volume, and that volume is going to be calculated by taking 4 pi multiplied by whatever this h is. And that h, by the way, that's what we're trying to solve for. So we know what the volume is. It's going to have to be equal to this number here. And so then we're just going to solve for h. And we get an answer. And that number differs from the height of water we were given before because the area of that cylinder, the area of the opening of it, does not match the area of the roof itself. Had we left this cylindrical tank just out in the yard somewhere and let the rain fall into it, then the height it would have increased would have been 17.3 millimeters. However, the area of our circular tank was going to be 4 pi, which is whatever, about like 12.566. If we were to take 4 pi, though, and divide it by the area of the tank, which is 65, these units are in square meters, that's going to get you the same answer as if you were to take our water level rising in the roof, so that's our 17.3, and dividing that by 89.5, which is the water level rising in the tank. Subject to rounding in the problem, which we did when we included pi here in our answer. those two values are going to be the same. So that's just another way that you could have solved this problem. The area of water collection is going to be inversely proportional to the height that the water level will rise within that area. Anyway, to close out this video, thinking about volume brought me to the following quotation by American literary historian and critic Thomas Lounsbury, who said, "We must view with profound respect the infinite capacity of the human mind to resist the introduction of useful knowledge." I think that by the word capacity here, he meant the ability of the human mind, because, of course, if he were referring to the size and dimensions of the mind, he should have said volume. It is the knowledge itself which would have a capacity. Regardless, dear viewers, please do not resist.